Okay, so last time at the end, I think I'm going to redo the example that I was doing at the end there, but maybe first we'll look at the semantics and then we'll try it again. So I probably should have had you all reading about scoping, and I guess maybe I sort of did. You have a reading assignment from the book. I still don't understand why my video is so slow. Does it seem okay to you?
It seems fine to me.
Okay. Um, so we were looking at this model of computer of programming language running on a computer with memory, where we have our variables, or they point through, the environment function takes as input a variable and returns a location, which is just a memory location, an address. And then the store is going to be a function that maps addresses to integer values. So we have this one level of indirection between, instead of variables going directly to integers as they did in the previous semantics, now we have this idea of memory in here. And so then we defined a type for environments as being something that maps a variable to a type of location, and locations are just an int, a synonym for integer. And then we also have a type called store, which is a map from locations to int. So those give us those two levels of maps. And procedures, which we're also going to define in this section or this chapter, we need to have a map that given a procedure name, which is just a string, returns a statement paired with the environment that was was in place at the time the procedure declaration was seen. And so we can think about an environment, an overall environment. We're going to need these maps from string, and if it's a variable, it's a map from string to location. If it's an environment, it needs to be a map from string to, and this is wrong, this should be statement and paired with environment. And so we're just putting them together in a record so that we can pass them around. Now we'll see below, you may not need all the environments all the times, but so you can leave them separated out like he does in the book. But once you start to add more of these things, you end up with kind of like an overflowing number of environments, and you have to choose the right ones to pass at which time. It's just maybe easier to make an environment, one environment that holds all these little sub environments in it. But that's that's a standard language in programming languages to call these maps from identifiers to whatever kind of thing the identifier is getting mapped to. Those maps are called environments. And then the store is also, like we said, a map from location to int. And last time we defined this allocate function. And what the allocate function does is you give it a store, and it does a few things. That what it returns is the next available location. So if you think of a store has, maybe 10, let's say, memory locations in it. When you call alloc, what you get back is a store that now has 11 memory locations in it, and the loc value will point to location 11. Well, they start at 0, so it was point to 10. So how do you do it? Well, you just take the old store, and the store keeps track of what's the next location that's available. So I take the store and I look up the next available location, and that is going to be my answer, L. And then you insert into the store has a location, which is in our implementation, the location -1, and you store L plus 1 in there. So now you've incremented the next location in the store. And so that gives you S double prime. And then into S double prime, you insert, you update the max store size, which is location -2 with, I don't know why this thing keeps blinking, but it location -2 gets updated with the maximum of either L plus 1, which is the next location, or whatever the previous maximum was. And then what you return is L, the next location, and the new store that has those two pieces of additional information properly set. So is there any question? Anyone have a question? Okay, so the new language syntax looks like this. We have assignment, we have a skip, we have the semicolon, we can do the sequencing operator, we can do a statement 1 followed by statement 2. We have the if then else, the while. And now we have a new one called begin, and it takes a list of declarations and a statement and then an end. And then we also have a way to refer to P's, which are procedures. So proc, if I want to define a procedure, that's part of the declaration. So declaration, you define the variable, and the variable will be allocated, new space for the variable will be allocated, and the map will be that X will point to the new location, and then that location in the store will actually be updated with the meaning of A. Now, when we declare a procedure, all we really do is bind P to S together with the environment that's currently in place. So last time we kind of went through this thing, and I don't know, I apologize, my notes were really ugly on that. So let's just look at some semantic equations, because there was some confusion. Maybe we were looking at what we were looking at was, what are the possible things that bindings that are referred to. And kind of surprising to me is that most of you, even though like in all the languages that you pretty much use, I don't know, there's maybe there in Perl this doesn't hold, in Python is lexically scoped. I don't know. So lexical scoping basically means that at the time the declaration is made, the only thing you need to look at is the things above that in the code. So when I write down proc q is call p, before I redefine p down here, it's decided at that time that this p refers to the previously declared procedure. And similarly for variables, if a variable in a block gets reallocated, then any declarations that are in the scope of that, like this procedure, those X's refer to this declaration, and this X refers to this declaration. But Q doesn't have anything to do with that X. Q calls P, and P is bound because of lexical scoping bound to X. Now we're going to discuss various strategies for doing this. But so I don't know, you probably can imagine what the semantics for A expressions looks like. But maybe not. I mean, they look so we're looking at the big step semantics, and can anyone tell me, why do I need the environment to evaluate an A expression, which is in this language here? Why would I need the environment? Is somebody talking and I can't hear? Nobody said anything. I mean, come on, we talked about this previously when we were talking about why you needed the state. Can you hear me? Somebody indicate that you can hear me.
Yeah, I can hear you.
We can hear you.
Okay, great. Now, why do I need, here's the old rule for states. Why do we need the state to evaluate an A expression?
Because it's mapped to something else. There's a function.
Well, the state is the function that maps variable names to ints. So why do I need it to evaluate an A expression?
So that's how you assign your variables actual values?
Right, correct. Thank you. Who said that?
Me, Addison.
Addison. Okay, thank you. Yeah, it's right here in the rule here. This is the rule for evaluating a variable. And if I want to say the variable X evaluates in the big step semantics for arithmetic to the value V if, and here's where I need the S. I need to use S to look up the value of X. And I get back V, and so this is what I write down. S turnstile X arrow sub A V, meaning the variable X using the state S evaluates to the value V. And so this was the derivation rule for that. So now our new rule is going to say, okay, we kind of separated this old map and this old store idea, took variables and went directly to integers. But now we have this intermediate idea. We say, oh, variables by the environment get mapped to a memory location, and then when you can use the store and figure out, given a memory location, what the value is in that store. So here we say X, in the big step semantics, given the environment env and the store sto, X evaluates to V if the environment of X is equal to L and the store of L is equal to V. So remember, environment's a function that remembers the memory location that a variable is bound to, and the store is a function that allows you to look up the value stored at a particular memory location. Now, the kind of annoying thing is that all the rules, even though this is the only rule that's actually going to use the environment and store pair, we have to carry it around for all the other ones, because how can we we have no way of magically directing it down just to the case X. Like, suppose we're doing one of these, an A1, let's say, plus A2 and A1. So here we get the environment store, we have to pass it down. In the numeral one, I mean, if we knew we're only evaluating a numeral, we don't need this. But what we're evaluating is an A expression that could turn out to be a numeral. And so we need the variable environment and the store, even though the semantics, kind of looking up the value of a numeral has nothing to do with the environment and store. We just pass it around everywhere. Now, we also have, we had environment and store. Here's A1 op, A2 arrow V. And so here we evaluate A1 in the environment and store to get back the value V1, and we evaluate A2 in the current environment store to get back the value V2, and then we apply the op. So this means do real addition on V1 plus V2 if this is the plus symbol in our syntax, our abstract syntax tree. And so then that looks like a V prime, but that's just V. Parentheses, you just go up. Now, what would happen? So the reason that we can pass the same environment store everywhere, we never modify the environment or the store when we're evaluating an arithmetic expression, is because for two things. One is there's no way to declare a new variable in the language of arithmetic expressions. We can't declare new variables. We can just refer to variables by mentioning their name. So I can mention the name of a variable, and that's going to be evaluated to a value by using the environment and store. So that's looking something up. And that's the only time the environment or store are used. So for example, and why is that the case? It's because we don't have any operation in our language that modifies the store. So this is truly a functional language. And let me see if I can make my my annotation thing work. So let's see, can I draw on this or no? Yeah. So does anyone know what the X does in C++?
Yeah, it increments it.
It increments what?
It increments x, increases x by 1.
Okay.
Changes the value of x to 1 more than its previous value.
Okay. And what does it evaluate to? What's the value? If I say y equals x in a C++ program.
The new value of x, I believe.
So if I have like
so it would increment
if
x.
I say x is equal to 7, and then I say y is equal to x++.
They're both 8. Wait. If x is 7, yeah, then they would both be 8.
Does anyone else want to challenge that? Thank you, Letitia, for speaking up.
I agree. That's what I was thinking it would be.
Okay. What about if I said, let me erase one of these things that I had here. What if I wrote down z gets the value of plus x?
Pretty sure plus x and x do the same thing.
Interesting.
I could be wrong though.
Yeah.
I don't remember. Haven't used C++ in a hot minute.
Okay.
Isn't it that they do the same thing, but the timing on when they increment is different?
Yes. So initially, I mean, I don't know. We don't have any value for z here. X is 7. Y has no value. And at the next step, we say y gets the value of x++. This is called the post increment operator. And so the value of the expression x++ is the value 7. So down here, y gets the value 7, but x gets incremented after the value is returned. So x now has the value 8. And then z gets the value of plus x, gives you back that z, look up the value of x, increment it by 1, and give that value to z, and then increment the value of x. So here's what you get after these expressions. So in this one, you increment before you just you increment the value of x, and that's what gets returned. And x has the side effect of also incrementing the variable, the the value stored in the memory location referred to by X. And then here, it's a post increment. So the increment happens after the value of this expression is the value of X before it gets incremented. So with that in mind, one thing we can see is that these operations, these plus plus operations, have an effect on the store. So let me go over here and just try to get out of this and go to my Emacs. And I'll erase all that. So let's just do, I don't know, this maybe I should just leave this for homework, but I guess I'll, that's awfully small, isn't it? I don't know, what the heck? Let me see if I can go to my terminal settings. This is probably going to break everything. I don't even see my terminal. Where is it? Screen display. There we go. That's about as low as that can go. So let me try that. Who knows what this is going to do? Okay. Well, it did. It made it bigger, didn't it? So we have this little language. A expressions are either numerals or they're variables or they're some A1, and I'll use $sign to stand for an arbitrary operation. And or suppose we say, oh, and there, this should be an X. And suppose we added X plus plus or X plus plus X to our language. So the in our new model, we have environment, comma, store, tells gives the meaning of a numeral, by looking up, translating the meaning of the numeral. So remember, a numeral is not an actual integer. A numeral is a sequence of digits representing a number, an integer. And so this is the translation of the digits in the numeral n into an actual integer. So probably it's something like a string. So, and then the other rule that we have for using the environment and store for an X is the one that we just saw. It goes to V if, and you can do it a little bit better. You can say sto dot env x equals V. So in other words, apply the env function first, And that will give you a location, and then look it up in the store, and that's the value. And so these rules, this rule, STO, comma, ENV, I'm gonna have to wait on this one actually until after we do the update rules to this is illustrating a point. So, you know, maybe I should say up here, you know, $sign is one of plus. It's actually like a character plus times minus. Okay, so if I want to figure out $1, A2, well, first you have to evaluate A1 and get it to go to V1. And then you have to evaluate A2 and get it to go to some value V2. And then this is V, where V is equal to V1 dollar, meaning of $sign, V applied to V2. Now, we can do this. You notice that the store, since the store can't change, or the environment can't change. Oh, I want it to be ENV store, not store. Not, I don't want to flip around my order of my arguments. So in the fact that the evaluating an expression can't change the store or the environment means that I can use the same store on both sides. But what if I want to evaluate something like, you know, let's say the environment says X has the value, I'm just going to write it like this. X has the value 7, and the store, I'm sorry, X is pointing to address 0, and address, the store says address 0 is equal to 7. And now suppose I wanted to evaluate X plus 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 X. So I don't know, can anyone see that there's an issue here that we can't really carry along as normal once we modify? So let me give you the rule for evaluating ENV. Well, geez, we have to change everything. And we'll see why as we try to say, okay, what could X plus plus mean? What does that evaluate to? Well, we'll say that evaluates to V if, because it's the pre-increment version, you get the value before, you could say this. But this isn't taking into account, this kind of rule here is not taking into account the fact that after this value is given, then the store is changed. So I need to say, how can I even do this? I have this similar thing. I can do this correctly. I could sort of say, okay, if I do a plus plus x, then I could look up x to get v, and then I could say, okay, the answer here is v plus 1. But what am I missing? What's not characterized by these rules? Which part of the meaning of the plus plus prefix and postfix operators is not captured here?
The new value in the store.
Right. So I don't even have a way of writing it down, really, because I only get back a value. So this is one of those cases where we'll have to go back and we'll have to say, okay, let's modify everything. We'll return a value together with the store to solve this problem. And for this, the store doesn't change. And for this, the store doesn't change. Let's skip that one for a minute because that gets really complicated. This one, we get back V, but we return, oh, okay, so up here though, I'm gonna have a similar thing. And so now we know, because we just fixed this, that the store is going to be the same store, but we don't know. It might be S1, but something different from the semantic. I mean, we could just say store here. And then down here, what do we want to do? We want to return the same value, but now I want to return the store where the location pointed to by X is increased. I'm sorry, the value stored in the memory location pointed to by X is increased by 1. So how do I get the location that's pointed to by X? I look it up in the environment. And what do I want it to be? I want it to be 1 more than V. So remember, STO with some square brackets, it's going to be just like the state. It's going to say, okay, what is E and V sub X? Is some location in memory, whatever. And I already determined the value of X. So this one just says, and so this store here is so we haven't changed the memory location pointed to by X. X still points to the same memory location. We haven't modified the environment, but we have, you know, so this is the store. And I think maybe this is maybe something that's confusing. Okay. So we captured the idea that postfix increment gives you the value of whatever X was. And but modifies the store to return the store where, so returns whatever, you know, the store where the location pointed to by X is incremented by 1. And so we're going to need to do the similar kind of thing down here. We're going to say this just returns store. And this returns V plus 1, and also the store where the location pointed to by X has the value V plus 1. Okay. And so now I can figure out the meaning of something like this. I can say, okay, but here's the problem. And this is an arbitrary thing. And once you add, see, before, when you don't have any possibility that an arithmetic expression has a side effect, which we had, that's what it was like before we added this. We didn't need to return the store. But now once we return the store, let's try and modify this rule for a minute. We say, okay, so this should be some like, you know, S. I'm going to need 2 of them. So do I say this is S1? And then I use S1 here to calculate S2. Well, that's one possibility, and it's perfectly okay. That means you would always evaluate the left sub-expression before you evaluate the right, because you need to get back a store. But you could do it the other way. And so it's kind of an interesting problem, is that once we do this, we've imposed, once expressions, arithmetic expressions, can have a side effect. In other words, they can change the value of the store, of the memory store. Then now we have to impose an order of evaluation on the thing, because we need to know, like, do I do A1 first and get back, you know, maybe I should call this STO1. and then use SDO1 to evaluate A2, or do I do it vice versa? Do I make it non-deterministic, but then you could get back non-deterministic results. You don't want that. I mean, you want this program here to have one meaning. So let's try to use these rules. I don't know. Somebody has to ask me a question. I know this isn't clear.
I just like to see it implemented with that example you have. That might clear it up for me.
Okay. So what we said was whenever we see a binary operator, and in this case we've got plus, do this one on the left and then do this one on the right using the store that results from that. So the first one we do is we do this, and then over on the other side we do something different, but roughly it looks like this. We don't know, you know, this is like a question mark. We don't know what that looks like yet. And I need to get rid of the left sub expression out of there. Now, let's evaluate the left side first. And so X++ says, first evaluate X in the same environment and store above. So X equals 0. And then 0 goes to 7. I mean, writing 0 equals 7 looks really ugly, but okay. I don't know. Should I write them like this instead? 0 gets mapped to 7. I mean, he uses a nice math symbol that I don't have access to. Something like that, right? But I'll just write 0 equals 7, even though it's potentially confusing. And then we evaluate. So we're doing this rule. Here it is. We're evaluating now the variable X. And to evaluate the variable X, we look up X in here. It gives us 0, address 0. Then we look up what's in address 0 and we get back 7. And so this returns the value 7 paired with the store that has not changed. And then down here, what I do is I display the same value that I just got, which was 7. And now I use the store where the location referred to by X has X plus 1. So this is the store 0 equals 8. And so now on this side, I use that store to evaluate this, and to evaluate this. I evaluate just X. And X goes to value 8. And the store that I return is just the one that, so now I'm doing this rule, which doesn't change the store, right? So this rule also returns 0, 8 as the store. And then down here, I'm using this rule just above, which says, okay, now take the value and add 1. So I get 9. And then return the store where the variable has been, the location, the value stored in the location referred to by X is now equal to whatever it was plus 1. So this becomes 9. And so now I think I didn't, this really, no, that returns STO2, and I'll write it over here, STO2. So now what do? Now I do the operation on 7 and 9. So I return the value 16 paired with the rightmost store. Now, do you think we get a different answer if we do the plus plus x plus x plus plus? Okay, so first of all, any questions?
Do you just use the rightmost store because it was the most recently updated on the final evaluation?
Yes, this was the most recently updated. That's why, yeah, but the rule says that, yeah, because I did this one and I got a store, and then I used STO1 here as the input or the store to use for evaluating A2. So down here, what we did was we took this store and we used this to evaluate plus plus X. And so then it got propagated up here. This doesn't change the value of the store, but the plus plus rule adds 1 to it, both to the value being returned here, the value being returned, and the value stored in the store. Let's do the other way. I don't know. Has anyone got a really quick? Do they see it? Do we get something different if we do this the other way? If I make this plus plus x and plus x plus plus. So when I go up here, now I'm doing plus plus x, and so then x is equal to 7, and down here x is equal to 8, and the new store has an 8, and so that means over here we use the new store that has an 8, but this is no longer that. This is x plus plus. And so I evaluate x and I get back the x, and it's an 08. And then here I return 8, and the store gets incremented by 1. And so now I have 8 and 8 is 16, and the store is equal to 9. So that's interesting. Like, you might break the commutative law of addition when you add this kind of thing in, but it didn't. If I did it right, I'm adding 8 with 8, and here I'm adding 7 with 9, but I still got the same answer. So we just proved, like, okay, even though the sub-expressions, the sub-derivations have different results, the final result is the same. Now we'd have to prove, if we wanted to actually prove this, we'd have to say, okay, we'd have to show that for every store, every environment, and every store. And then you run into the problem of, well, you know, what if you wrote down something like this? What if you say, okay, ENV and some store, you got some environment one and some store one. And then you say, you know, plus plus Z. What do you do if Z is not in the environment? What would you like to do?
Just assign it 0, maybe.
Okay, there's a good answer from someone who likes, you know, untyped programming. Just give it an arbitrary, I mean, 0. Why 0? 0, 0's false in C and C++. I don't know. 0's, you know, 0 could be a good answer, and it is an answer that's selected.
Isn't it like a kind of a standard in a computer science that if you like return a 0 or something, it means there was a failure?
Well, yeah, except that here's the problem. What if my environment said X is at location 0? And my store says, okay, location, I like this notation better. I think that 0 has, you know, let's say 7 in it. And so now you're saying, like, if I mean, are you saying that if ENV Z, if Z is not in, so the proposal, I think, is if Z is not in X equals 0, which it's not, then Z equals 0. But then that means that, so now we have kind of like this default thing that, okay, Z is equal to 0. It's the same thing if it's not there as if it is 0. And then we say, okay, now evaluate Z. What does Z go to? Okay, Z goes to 7. And so what is plus plus? Well, 7 together with the store 0, comma, colon 7. And so then that means plus plus Z, according to its semantics, evaluates to 8 and 0, colon 8. And to me, this, do you see what's wrong here? That means if you had, like, you know, okay, if you declare a variable, let's say X, and you set it 7, and then the next thing you do is you say, I mean, I'm even having trouble figuring out what if I say Y, which is undeclared location, well, let's make Y a value. Let's just say we declared Y even. I can't remember if it's, I think it's for the on the declaration, I think it's just a semicolon. And now if I said Y gets the value of Z plus plus, can anybody see what's going wrong? What happens here? So this is the kind of thing I was working on last time, and I didn't do a very good of displaying it. So the environment before we start the program is the empty environment, and the store before we start the program is the empty store. And so after I've executed this expression, I've got X is going to location 0, and in the store I've got X, or I'm sorry, a 0 gets mapped to 7. And then here in my environment now, I add that X equals 0 and Y equals 1. That's the next available memory location. And then over here, the store is 0 gets the value 7. Oh, that's not a 0. 0 gets the value 7. And 1 gets the value 0. Are you with me? Yes, yes.
Oh, yeah.
And so now this one doesn't change the environment at all. Except that, it's kind of like a ghost that says, oh, Z equals 0. And so this is kind of like, ghost environment. Whenever you need to choose a sort of an arbitrary value like that, you got to try to figure out, okay, what happens with 0 and what happens with 42? And so now what happens here is though that the new store after I execute this is Z is 0. So I update the store at location 0 with the value of Z plus plus. So that's the value. Oh, all right. Let me do plus plus Z. Yeah. And so now this becomes an 8. I guess it doesn't matter either way. Z plus plus was fine. Okay, so now here's a program where we started out with declaring variables X and Y, and then we reference Z, and all of a sudden the location, the value, the variable X has changed because X points to 0, location 0, and we, by executing this with Z in the environment equal to 0, now all of a sudden X has the value 8. That'd be a program that would be if you had this kind of semantics, it would make your programs very, very, very difficult to debug. Do you agree?
Yeah, that was a terrible idea.
You know, sometimes there's kind of like two good answers, and one is that, well, if you get to runtime and you see this, and this is what so-called dynamic languages will do that are untyped, is they just crash. But maybe the thing to do was not this. Maybe the default behavior when you see an undeclared variable was to call alloc and to say z, give it the next location, which is 2. And then you've got some new memory location here, but you don't have any default value. So now you got to do location 2 has, again, we got to guess something. What do you want to put there? Okay, let's put 42 in there. Location 2 has 42. And so what happens then when this z++ is incremented, it becomes a 43. So maybe that's better. Like if you see an undeclared variable name, just allocate it and give it some default value. Maybe we want it to be, maybe you want it to be 0, which means after this thing is executed, it's a 1. So now there's two good answers of how we could fix this. One is we could type check our programs before we try to evaluate them. And we can check whether or not there's any undeclared variables in a program. That's easy to do with type checking. And the other thing we can do is we could just crash the program. Like somebody should know, this can't be actually a correct program. So just crash it. Make them suffer. Or you could give a syntax, I mean, the type checker is really the one that finds it, but you could give it is kind of like it's a very weak form of type checking. Okay. Questions? Oh, something's in the chat. -1. Yeah, right. Then you'd clobber the next location value. That's not good. -3 could be a junk location. All right. Or type checking. Type checking is a good vote, I think, because it's not hard to do. It's linear in the size of the program, so it doesn't add very much to the So like the compile time to do the type checking is pretty minimal, and you rule out bad programs. So, all right, well, that's great. I even managed to end on time. So I'll throw up a homework. Maybe I'll ask you to implement this thing I just wrote out, like in Haskell. All right. See you all Tuesday.
Thank
Or-
you.
Yep. So long.
Thanks.